Integrals with square roots are a special class of complex integrals because the square root function is multivalued. For example, the square root of 4 is plus or minus 2, and these two are two separate values. In complex number theory, these multiple values take you to two different branches of the complex plane. And so you have to consider what are known as branch cuts. The complex valued function root z is a multiple valued function, and the branches originate at z equal to 0. So z equal to 0 is a branch cut. Even though this denominator does not vanish, or seemingly only vanishes at z equals plus or minus I, the fact that you have a square root makes this a more interesting contour integral. So what we're going to do is we're going to choose a contour which goes around this branch. So I'm going to take the origin and surround it with a cut that extends to all the way to the right up to a certain radius, and my circle is going to look more like an ellipse because of the way I've drawn the complex plane, unfortunately. So that's going to be your contour, sort of like a Pac-Man. Now that's the contour C. We're going to call this, it goes like this, and then it comes in, goes around, and comes back out. You can see that there's some sort of a cancellation effect here, but we have to be careful. We can't make such irresponsible statements in complex analysis. So let's be careful there. Now, if this is made into a z, z equals plus or minus I are going to be the simple poles. So I'll put that over here. And so that's the situation we have in the complex plane. Let us write the integral as the complex integral has the integral around this curve, complex contour C, root z over 1 plus z squared dz. The denominator becomes 0 at e to the I pi by 2, which is another way of saying I, and e to the minus e to the I 3 pi by 2, or at I n minus I. So those are the two simple poles. So this function, which I'm going to write as f of z, is just z to the power half divided by the factorization of this. So I get z plus I times z minus I. And now by the theorem of Cauchy, the integral of f of z dz is just going to be the sum of the residues around these poles times 2 pi I. So that's going to be 2 pi I times these are just simple poles, so the residues are got by multiplying the residue at I is got by multiplying the whole thing by z minus I. So it's a limit z goes to I, z minus I times f of z plus the limit as z goes to minus I, z plus I times f of z. The simple pole recipe has to be used. So that's 2 pi I. Let us now, if I multiply this by z minus I, that goes away, and I just have I to the power half divided by I plus I. And here, when z is equal to minus I, that becomes negative I to the power half divided by negative I, negative I. Now, the square root of I, one way of thinking about the square root of I is e to the I pi by 2. First, let's find out what e to the pi by 2 is. It's cosine pi by 2 plus I sine pi by 2. So in other words, it's just I. So the square root of I is just e to the I pi by 4. because it's 1/2 of that, e to the 1/2 of that. So now I can just simplify this. That's going to be 2 pi I. E to the I pi by 4, however, is cosine pi by 4 plus I sine pi by 4. So that's going to be 1 over root 2 plus I over root 2. So let's write this as 1 over root 2 plus I over root 2 divided by 2I, and that's going to give me the same thing with the minus sign. So the minus sign will only affect the sine term. So I get 1 over root 2 minus I over root 2 divided by minus 2I. So that takes care of the plus sign here. So I get 2I. And you notice that this term just cancels out. So I get this 2 cancels this out, and the I cancels that out. So I just get root 2 times pi. So I get 2 times 1 over root 2, which is root 2 times pi. That's my answer. Now the trick with doing complex integrals is to next write this f of z, integral of f of z around this closed contour, as a sum of parts, most of which will vanish except for the desired integral. So the 1/2 of it is to use Cauchy's residue theorem to evaluate the actual contour integral. The other half of the story is to write the contour integral itself as a sum of parts, most of which vanish except for the desired integral. So let's do that part. So here I'm going to write the integral f of z dz, which we have just evaluated, as the integral over the upper half plane and the lower half plane, because they have the same kind of arguments, f of z dz, plus the integral gamma 1 integral gamma 2 f of z dz. Now you see the danger in rashly saying that this was just opposite of that. It's not, because this is what's going to give us the answer, because this we're going to make it vanish. Now the bounds, we're going to have the same type of argument for the bounds as we always have had. You put z equals rho e to the I theta and then take rho to infinity. So by the Cauchy-Schwarz inequality, f of z dz, the integral of that is going to be less than or equal to the integral of the absolute value of f of z dz. And then the absolute value of f of z, which is all this, when you substitute this rho equals e to the I theta, becomes root rho, root z is root rho, times e to the I theta over 2. And then when I take the derivative of this dz, it becomes I rho e to the I theta d theta. So that's just rho I e to the I theta d theta divided by 1 plus z squared, and that's rho squared e to the 2I theta. Now as before, we want to make this integrand independent of theta, so we'll use the maximum value of 2I theta. 2I theta, the maximum value is 1. E to the 2I theta is cosine 2 theta plus I sine 2 theta. The maximum value of that is 1. So I'll just, well actually I need the minimum value because I want to make the denominator as large as possible. So this is going to be less than or equal to the integral from 0 to 2 pi of, here I get rho to the 3/2 because I have root rho and rho, and then that's just d theta, all the absolute values of e to the I, theta over 2I, etc. It's just 1, divided by rho squared minus 1. Actually it's 1 minus rho squared, which you can write as rho squared minus 1. And this can be evaluated. It's just rho to the 3/2 over rho squared minus 1 times 2 pi, which goes to 0 as rho goes to infinity. So we have done with that expanding contour argument. Now the integral over the gamma 1 is going to be the integral from 0 to infinity. I'm going to now put z equals r e to the I theta. So that's just going to be x plus, well, if I write this as r e to the r, let me write this, z as equal to r e to the I theta with theta equals 0, because you want this to be along the x-axis. So that's going to give me r to the half dr over 1 plus r squared. For gamma 2, however, we have to consider z equals r e to the I pi, because it's gone around. So I did 2 pi, because it's gone around by a 2 pi angle. So that gives me the integral from infinity to 0 e to the I pi. When I take the square root of this, I get r square root of r e to the I pi, because square root of e to the 2 I pi is e to the I pi, and then the derivative of this dz, and that's just going to give me e to the 2 pi I times dr divided by the denominator, and that's just 1 plus z squared, which is r squared e to the 4 pi I. So this quantity here, when I multiply everything through, this just gives me negative, because e to the I pi is minus 1. Also the negative sign I'll get from, the negative sign I'm going to get from flipping. And then e to the I pi is equal to, e to the 2 pi I is 1, e to the I pi is just cosine pi plus I sine pi, that's just minus 1, so that will cancel out the minus there. And then I get square root of r over 1 plus r squared, because e to the 4 pi I is just equal to 1. The upshot is that the integral from the gamma 1 and the gamma 2 are the same. So when I put all this in this equation, which I'll call star, the value of evaluation of star has already been done. It's root 2 pi. Therefore, 2 times our desired integral 0 to infinity root x over 1 plus x squared dx is equal to root 2 pi, and therefore our actual integral from 0 to infinity root x over 1 plus x squared dx equals root 2 pi over 2. Keep that in mind, because we're going to evaluate the same integral using a different method, and this method does not involve complex analysis. Now, in the old textbooks, you will find sometimes the word elementary used. Elementary does not mean easy by any means. Elementary simply means that you don't invoke any complex analysis in the argument. So one way to do this integral is actually to use what's called a u substitution. So we're going to try that. This integral is not easy by any means. What I'm going to show you now is one of the hardest integrals you can possibly do using elementary techniques. So don't get your hopes up. The integral from 0 to infinity root x of 1 plus x squared dx. The first thing we'll do is put x equal to u squared. That will get rid of the square root, but it will bring other problems. So 2u du will be equal to dx then. The limits will continue being from 0 to infinity, so the integral will be the integral from 0 to infinity 2u squared, because I have 2u from there and the u from here, du divided by 1 plus u to the 4. Now what is that? That's a monster. We have traded one headache for another. How do you do this? Well, the trick is this, and this is a trick I'll forgive you for not guessing. You have to factor the denominator. So this factors out actually like this. You can reverse FOIL it and show that this is true. Once you do that, you can write it in terms of partial fractions. I'm going to sketch the details. I won't do every tiny detail for you, because it's very time consuming and it's rather trivial to actually do all these separate details. So you just end up doing partial fractions, and when you do partial fractions, this gives me 1 over root 2 u over u squared minus root 2u plus 1 minus 1 over root 2 u over u squared plus root 2u plus 1. So that's what you get, and you can quickly verify that this is true, because if I multiply this through, I get u cubed plus root 2u squared plus 1, and then I get minus u cubed. Again, I get plus root 2u squared, so I get this root 2 factor which cancels this factor, and then that u squared and u squared gives me 2u squared, and the one term cancels just as the u squared term cancels. So this actually works. Now we can write our integral as a sum of these two integrands. So I'll have 1 over root 2, the integral of u du divided by u squared minus root 2u plus 1 minus 1 over root 2, the integral of u du divided by u squared minus root 2u plus 1. Now at this point, I realize the denominator is got a derivative that's kind of like the numerator, except not quite. The derivative of the denominator is 2u minus root 2. So I'll make it happen. One way to make it happen is to divide by 2 first, and then write it as 2u. Well, I have 2u, but I don't have root 2. So I'll manufacture that by adding and subtracting it. And then I have the denominator as is. And here, the next term, I'll do the same thing. That's 1 over 2 root 2, the integral of 2u. But here I need, where was this? This is wrongly written. So here I need 2u plus root 2. So I need to manufacture a root 2 like this by adding and subtracting. That's a du there. Almost there, believe it or not. So this integral can be split up into two parts. One is 2u minus root 2 du over u squared minus root 2u plus 1. And then I have the other integral, which is root 2, which I can cancel with this root 2, so that just gives me 1/2. The integral of du over u squared minus root 2u plus 1, and I'll do the same treatment for the other one. 1 over 2 root 2 integral 2u plus root 2 du divided by u squared plus root 2u plus 1, and then I have a minus of a minus, which is plus 1 over 2 integral du over u squared plus root 2u plus 1. So again, this is just elementary stuff. If the bottom is called w, let's say, the numerator is dw, so that's just going to give me 1/2 over 2 root 2 natural log of w, which basically is u squared minus root 2u plus 1. So I've done that integral. Now this integral, I can factor this u squared minus root 2u plus 1 as a perfect square. Let me do that here. So that gives me du over, that's u minus root 2 over 2 squared. So when I square this, I get u squared minus root 2u plus root 2 over 2 squared, which is half. So I have to subtract that half, which makes this half, because 1 minus half is half. So that gives me half. And this one, by the same token, is 1 over 2 root 2, natural log of u squared plus root 2u plus 1. And then here I again complete the square like I did for this one. So that's du over u plus root 2 over 2 squared plus half. So you can see it's not that bad, but it's kind of yucky. And here I'll combine these two by using the property of logarithms. So that's u squared minus root 2u plus 1 divided by u squared plus root 2u plus 1. And then these are just arctangents, so that's easy to do. It's 1 over 2, and then I get root 2 tan inverse u minus root 2 over 2 over 1 over root 2. Technically I should put the absolute value sign, but I'm not going to do it. And then I have plus 1 over 2 root 2 tan inverse of u plus root 2 over 2 over 1 over root 2 plus c, but I'm going to evaluate all this from 0 to infinity. Next. Now here, by L'Hopital's rule, you can show that that's 0. I won't bother doing it, but you can show that that limit is simply 0. So all I have to worry about is this and that, and they contribute only at infinity. Let's see why. So I get root 2 over 2. That's going to be tan inverse infinity, plus that's also going to be tan inverse infinity, minus root 2 over 2. When u goes to 0, that's tan inverse negative 1. And that's going to be tan inverse positive 1. Fortunately, these cancel out. So you don't get any contribution from these. So that's going to be root 2 over 2. Tan inverse infinity is pi over 2. Tan inverse infinity is pi over 2. So the whole thing is pi. And that leads to the exact same answer that we had through the complex analysis method. So the elementary technique and the complex techniques match up. Now, this elementary technique is not quite elementary. It's a lot of work, but mathematicians call anything that does not use complex analysis elementary.